Queen to e5.
That's totally barbaric.
That's wizard's chess.
Hi, my name is Samantha, and I'm a junior studying mechanical engineering.
Hello, my name is Grace True, and I'm a biomedical engineer.
I'm Yvonne, a freshman majoring in mechanical engineering.
Hello, my name is Pooja, and I'm a freshman studying electrical and computer engineering.
Hi, my name is Laurent, and I'm a sophomore majoring in electrical engineering.
Hi, I'm Pilar, and I'm a sophomore studying CECS.
Hello, I'm Yashvi. I am a sophomore studying CSBA.
Hi, my name is Shivani, and I'm a junior majoring in CECS.
Hey, I'm Delara. I'm a junior studying CECS, and I was the project manager for this team. So our team's goal was to create a real-life version of Wizard's Chess from Harry Potter, and we did this by building off a project from last semester, Smart Tic-Tac-Toe. So the Tic-Tac-Toe board established a really good foundation for us in terms of mechanical setup, electrical components, and a high-level software structure, so that this semester we could just dive right into improving this design and implementing the more complicated game of chess.
So our chessboard follows the same basic design specifications as the Smart Tic-Tac-Toe board from last semester. So we used a pulley system, which avoids having a stepper motor mounted onto a linear slider. And then we improved this design by adding tensioners, which reduced the slippage of the pulleys, which made a more steady and precise structure. And then we also increased some of the dimensions of these parts just to make the ease of assembly a little bit better and make it easier to change and make modifications if needed in real time.
So to create the effect that the chess piece is breaking once it's been captured by an opponent, we decided to reverse the electromagnet's polarity that traverses underneath the chessboard and controls movement of each chess piece. Once the chess piece is captured, we will reverse the polarity, and that'll set off a chain reaction that makes the piece look like it's exploding or falling apart. And in this GIF over here, you can see we have the magnet sitting in the base of each piece, and as the polarity changes, the magnet shoots upwards in a hollow channel in each chess piece base, and it will basically cause the chess piece to fan apart and basically fall apart like it's breaking. And now Yvonne will talk a little bit more about how this mechanism works.
So our final mechanism consisted of 3 3D printed pieces, the 2 halves of the chess piece and the base. The magnet in the base of the chess piece is attracted to the electromagnet in order to move around on the board. And when the polarity of the electromagnet is reversed, the magnet is repelled by it and flips onto its other side, where it is once again attracted to the electromagnet. During this flipping action, the magnet pushes the 2 breakaway pieces, which flip over and opens up the chess piece.
So the electrical components we're using for chess are largely the same as what we did for tic-tac-toe. We're controlling 2 stepper motors underneath the board through driver boards interfacing with a Raspberry Pi, and we're controlling the electromagnet that moves underneath the board to attract the pieces with magnets in them with power relay boards. And we're getting all the different voltages we need to power our components through a handy-dandy multi-output power supply. The only difference this time is that we're using 2 power relay boards instead of 1, so that in addition to turning the electromagnet on and off, we can also switch the current going through it in order to reverse its polarity and repel the magnets above when we want to break a piece open.
Last semester, Smart Tic-Tac-Toe already set up most of the framework for the movements we needed to do this semester, but the movements were not quite precise enough to work with the chess pieces, since there's much less room for error on our new board. In order to fix the movement errors, we decided to use a color sensor with a calibration mat underneath the board so that we could dynamically calibrate our movements by detecting color changes in any of the 8 directions of movement. The calibration pattern was inspired by this gingerbread house, with the original goal being to create color transitions along the vertical, horizontal, and diagonal directions. However, after spending a significant amount of time writing calibration algorithms for our color sensor, we realized that the reason we did not have precise movements in the first place is because one of our drivers was wired wrong, and so only half of our motors actually worked properly. It's a small miracle that Smart Tic-Tac-Toe worked well enough last semester, even with the broken driver, but now that the broken driver is fixed, the color sensor is not really needed, it's just an extra redundant measure.
It's Pooja again, and I'll be talking us through the motor control flowchart. To begin, the players will place the pieces manually on the board, and the motors will do an initial calibration to determine board size. Then for each move in the game, we'll move the electromagnet to the piece's initial location, determine whether it's capturing the piece, which will be determined by the software backend, and if not, move to the final location. If we are capturing the piece, there's a couple of extra steps where we move directly next to the piece being captured, move the electromagnet directly under the captured piece, and reverse the polarity so that the piece breaks apart, just as we saw with mechanical earlier. Then we move back to the capturing piece, delay until its path is cleared by the players, and move it into its final location.
We built the front end of Wizard's Chess.
So we have two modes. So you can play against the AI, where the AI talks to the backend and returns moves automatically, or you can play against a friend.
When you play against the friend, you're going to have the option to pick a house for player 1 and player 2.
And it creates a board that is based on the houses that you choose.
You can move the pieces on the board through clicking and placing, and this communicates with the backend, which checks move validation. Or you can move the pieces with voice command, which we'll demo later.
We built this using React, and we used a couple of libraries to help us with the voice recognition.
We created objects and classes to represent each of the pieces, and this is how we embedded the SVGs and the images in them. These pieces would move across the board as we clicked, and that's how we changed the state of the board with the chess piece movement.
As for our backend, we're running a Flask server on our Raspberry Pi that receives HTTP requests every time a player attempts to make a move in the front end. We're using the Python chess library to validate moves, so if the backend finds that the move is legal, it will send the OK back to the front end, so the piece will be moved on the web app, as well as invoke the motor control code to physically move the chess piece on the board. We're also using Python chess to access the Stockfish chess engine to generate moves in response to the user when playing in AI mode.